A gyroscope is a device for measuring or maintaining orientation, based on the principles of angular momentum. Mechanical gyroscopes typically comprise a spinning wheel or disc in which the axle is free to assume any orientation. Although this orientation does not remain fixed, it changes in response to an external torque much less and in a different direction than it would with the large angular momentum associated with the disc's high rate of spin and moment of inertia. The device's orientation remains nearly fixed, regardless of the mounting platform's motion, because mounting the device in a gimbal minimizes external torque. Gyroscopes based on other operating principles also exist, such as the electronic, microchip-packaged MEMS gyroscope devices found in consumer electronic devices, solid-state ring lasers, fiber optic gyroscopes, and the extremely sensitive quantum gyroscope. Applications of gyroscopes include inertial navigation systems where magnetic compasses would not work or would not be precise enough, or for the stabilization of flying vehicles like radio-controlled helicopters or unmanned aerial vehicles. Due to their precision, gyroscopes are also used in gyrotheodolites to maintain direction in tunnel mining. Description and diagram. Within mechanical systems or devices, a conventional gyroscope is a mechanism comprising a rotor journal to spin about one axis, the journals of the rotor being mounted in an inner gimbal or ring. The inner gimbal is journaled for oscillation in an outer gimbal for a total of 2 gimbals. The outer gimbal or ring, which is the gyroscope frame, is mounted so as to pivot about an axis in its own plane determined by the support. This outer gimbal possesses 1 degree of rotational freedom and its axis possesses none. The next inner gimbal is mounted in the gyroscope frame so as to pivot about an axis in its own plane that is always perpendicular to the pivotal axis of the gyroscope frame. This inner gimbal has 2 degrees of rotational freedom. The axle of the spinning wheel defines the spin axis. The rotor is journaled to spin about an axis, which is always perpendicular to the axis of the inner gimbal. So the rotor possesses 3 degrees of rotational freedom and its axis possesses 2. The wheel responds to a force applied about the input axis by a reaction force about the output axis. The behavior of a gyroscope can be most easily appreciated by consideration of the front wheel of a bicycle. If the wheel is leaned away from the vertical so that the top of the wheel moves to the left, the forward rim of the wheel also turns to the left. In other words, rotation on one axis of the turning wheel produces rotation of the third axis. A gyroscope flywheel will roll or resist about the output axis depending upon whether the output gimbals are of a free or fixed configuration. Examples of some free output gimbal devices would be the attitude reference gyroscopes used to sense or measure the pitch, roll and yaw attitude angles in a spacecraft or aircraft. The center of gravity of the rotor can be in a fixed position. The rotor simultaneously spins about one axis and is capable of oscillating about the 2 other axes, and, thus, except for its inherent resistance due to rotor spin, it is free to turn in any direction about the fixed point. Some gyroscopes have mechanical equivalents substituted for one or more of the elements. For example, the spinning rotor may be suspended in a fluid, instead of being pivotally mounted in gimbals. A control moment gyroscope is an example of a fixed output gimbal device that is used on spacecraft to hold or maintain a desired attitude angle or pointing direction using the gyroscopic resistance force. In some special cases, the outer gimbal may be omitted so that the rotor has only 2 degrees of freedom. In other cases, the center of gravity of the rotor may be offset from the axis of oscillation, and, thus, the center of gravity of the rotor and the center of suspension of the rotor may not coincide. History. Essentially, a gyroscope is a self-balancing spinning toy, put to instrumental use. Tops were invented in many different civilizations, including classical Greece, Rome, Indus and China, and the Maori culture 1,000 years later. Most of these, though using the same conservation of angular momentum as a gyro, were not utilized as instruments. The first known use of such a top as an instrument came in 1743, when John Serson invented the whirling speculum, a spinning top that was used as a level, to locate the horizon in foggy or misty conditions. The instrument, used more like an actual gyroscope, was made by German Johann Bohnenberger, who first wrote about it in 1817. At first he called it the machine. Bohnenberger's machine was based on a rotating massive sphere. In 1832, American Walter A. Johnson developed a similar device that was based on a rotating disc. The French mathematician Pierre-Simon Laplace, working at the École Polytechnique in Paris, recommended the machine for use as a teaching aid, and thus it came to the attention of La copyright on Foucault. In 1852, Foucault used it in an experiment involving the rotation of the Earth. It was Foucault who gave the device its modern name, in an experiment to see the Earth's rotation, which was visible in the 8 to 10 minutes before friction slowed the spinning rotor. In the 1860s, the advent of electric motors made it possible for a gyroscope to spin indefinitely. This led to the first prototype heading indicators, and a rather more complicated device, the gyrocompass. The first functional gyrocompass was patented in 1904 by German inventor Hermann Ancher 1/4 TZKMV. The American Elmer Sperry followed with his own design later that year, and other nations soon realized the military importance of the invention in an age in which naval prowess was the most significant measure of military power, and created their own gyroscope industries. The Sperry Gyroscope Company quickly expanded to provide aircraft and naval stabilizers as well, and other gyroscope developers followed suit. In 1917, the Chandler Company of Indianapolis created the Chandler Gyroscope, a toy gyroscope with a pull string and pedestal. Chandler continued to produce the toy until the company was purchased by TEDCO Incorporated in 1982. The Chandler toy is still produced by TEDCO today. In the first several decades of the 20th century, other inventors attempted to use gyroscopes as the basis for early black box navigational systems by creating a stable platform from which accurate acceleration measurements could be performed. Similar principles were later employed in the development of inertial guidance systems for ballistic missiles. During World War II, the gyroscope became the prime component for aircraft and anti-aircraft gun sights. After the war, the race to miniaturize gyroscopes for guided missiles and weapons navigation systems resulted in the development and manufacturing of so-called midget gyroscopes that weighed less than 3 ounces and had a diameter of approximately 1 inch. Some of these miniaturized gyroscopes would reach a speed of 24,000 revolutions per minute in less than 10 seconds. 3-axis MEMS-based gyroscopes are also being used in portable electronic devices such as Apple's current generation of iPad, iPhone and iPod Touch. This adds to the 3-axis acceleration sensing ability available on previous generations of devices. Together these sensors provide 6-component motion sensing. Acceleration for X, Y, and Z movement, and gyroscopes for measuring the extent and rate of rotation in space. Properties. A free gyroscope maintains its axis. Gyroscopes can be used to construct gyrocompasses, which complement or replace magnetic compasses, to assist in stability or be used as part of an inertial guidance system. Gyroscopic effects are used in tops, boomerangs, yo-yos, and powerballs. Many other rotating devices, such as flywheels, behave in the manner of a gyroscope, although the gyroscopic effect is not being used. When the gyroscope is not free, it exhibits a number of behaviors including precession and nutation. The fundamental equation describing the behavior of the gyroscope is where the pseudo-vectors I and L are, respectively, the torque on the gyroscope and its angular momentum, the scalar I is its moment of inertia, the vector I per mil is its angular velocity, the vector I plus or minus is its angular acceleration, d is the differential in an inertial reference frame and d is the differential in a relative reference frame fixed with the gyroscope. It follows from this that a torque I applied perpendicular to the axis of rotation, and therefore perpendicular to L, results in a rotation about an axis perpendicular to both I and L. This motion is called precession. The angular velocity of precession I copyright P is given by the cross product. Precession can be demonstrated by placing a spinning gyroscope with its axis horizontal and supported loosely at one end. Instead of falling, as might be expected, the gyroscope appears to defy gravity by remaining with its axis horizontal, when the other end of the axis is left unsupported and the free end of the axis slowly describes a circle in a horizontal plane, the resulting precession turning. This effect is explained by the above equations. The torque on the gyroscope is supplied by a couple of forces, gravity acting downward on the device's center of mass, and an equal force acting upward to support one end of the device. The rotation resulting from this torque is not downward, as might be intuitively expected, causing the device to fall, but perpendicular to both the gravitational torque and the axis of rotation, that is, about a vertical axis, causing the device to rotate slowly about the supporting point. Under a constant torque of magnitude I, the gyroscope speed of precession I copyright P is inversely proportional to L, the magnitude of its angular momentum, whereas the angle between the vectors I copyright P and L. Thus, if the gyroscope spin slows down, its angular momentum decreases and so the rate of precession increases. This continues until the device is unable to rotate fast enough to support its own weight, when it stops precessing and falls off its support, mostly because friction against precession causes another precession that goes to cause the fall. By convention, these three vectors, torque, spin, and precession, are all oriented with respect to each other according to the right-hand rule. To easily ascertain the direction of gyro effect, simply remember that a rolling wheel tends, when it leans to the side, to turn in the direction of the lean. Variations. Gyrostat. A gyrostat is a variant of the gyroscope. It consists of a massive flywheel concealed in a solid casing. Its behavior on a table, or with various modes of suspension or support, serves to illustrate the curious reversal of the ordinary laws of static equilibrium due to the gyrostatic behavior of the interior invisible flywheel when rotated rapidly. The first gyrostat was designed by Lord Kelvin to illustrate the more complicated state of motion of a spinning body when free to wander about on a horizontal plane, like a top spun on the pavement, or a hoop or bicycle on the road. Kelvin also made use of gyrostats to develop mechanical theories of the elasticity of matter and of the ether. These theories are of purely historical interest today. In modern times, the gyrostat concept is used in the design of attitude control systems for orbiting spacecraft and satellites. For instance, the Mir space station had 3 pairs of internally mounted flywheels known as gyrodons or control moment gyros. In physics, there are several systems whose dynamical equations resemble the equations of motion of a gyrostat. Examples include a solid body with a cavity filled with an inviscid, incompressible, homogeneous liquid, the static equilibrium configuration of a stressed elastic rod in elastica theory, the polarization dynamics of a light pulse propagating through a nonlinear medium, the Lorentz system in chaos theory, and the motion of an ion in a penning trap mass spectrometer. MEMS, a MEMS gyroscope takes the idea of the Foucault pendulum and uses a vibrating element, known as a MEMS. The MEMS-based gyro was initially made practical and producible by Systran Dunner Inertial. Today, SDI is a large manufacturer of MEMS gyroscopes. FOG, a fiber optic gyroscope, is a gyroscope that uses the interference of light to detect mechanical rotation. The sensor is a coil of as much as 5 km of optical fiber. The development of low-loss single-mode optical fiber in the early 1970s for the telecommunications industry enabled the development of Sarnak effect fiber optic gyros. HRG, the hemispherical resonator gyroscope, also called wine glass gyroscope or mushroom gyro, makes using a thin solid-state hemispherical shell, anchored by a thick stem. This shell is driven to a flexural resonance by electrostatic forces generated by electrodes which are deposited directly onto separate fused quartz structures that surround the shell. Gyroscopic effect is obtained from the inertial property of the flexural standing waves. VSG or CVG, a vibrating structure gyroscope, also called a Coriolis vibratory gyroscope, uses a resonator made of different metallic alloys. It takes a position between the low-accuracy, low-cost MEMS gyroscope and the higher accuracy and higher-cost FOG. Accuracy parameters are increased by using low intrinsic damping materials, resonator vacuumization, and digital electronics to reduce temperature-dependent drift and instability of control signals. High-quality wine glass resonators are used for precise sensors like HRG or CRG. DTG, a dynamically tuned gyroscope, is a rotor suspended by a universal joint with flexure pivots. The flexure spring stiffness is independent of spin rate. However, the dynamic inertia from the gimbal provides negative spring stiffness proportional to the square of the spin speed. Therefore, at a particular speed, called the tuning speed, the two moments cancel each other, freeing the rotor from torque, a necessary condition for an ideal gyroscope. London moment. A London moment gyroscope relies on the quantum mechanical phenomenon, whereby a spinning superconductor generates a magnetic field whose axis lines up exactly with the spin axis of the gyroscopic rotor. A magnetometer determines the orientation of the generated field, which is interpolated to determine the axis of rotation. Gyroscopes of this type can be extremely accurate and stable. For example, those used in the gravity probe B experiment measure changes in gyroscope spin axis orientation to better than 0.5 milliarcseconds over a 1-year period. This is equivalent to an angular separation the width of a human hair viewed from 32 kilometers away. The GPB gyro consists of a nearly perfect spherical rotating mass made of fused quartz, which provides a dielectric support for a thin layer of niobium superconducting material. To eliminate friction found in conventional bearings, the rotor assembly is centered by the electric field from 6 electrodes. After the initial spin-up by a jet of helium which brings the rotor to 4,000 rpms, the polished gyroscope housing is evacuated to an ultra-high vacuum to further reduce drag on the rotor. Provided the suspension electronics remain powered, the extreme rotational symmetry, lack of friction, and low drag will allow the angular momentum of the rotor to keep it spinning for about 15,000 years. A sensitive DC squid magnetometer able to discriminate changes as small as 1 quantum, or about 2A, 10 or 15 WB, is used to monitor the gyroscope. A precession, or tilt, in the orientation of the rotor causes the London moment magnetic field to shift relative to the housing. The moving field passes through a superconducting pickup loop fixed to the housing, inducing a small electric current. The current produces a voltage across a shunt resistance, which is resolved to spherical coordinates by a microprocessor. The system is designed to minimize Lorentz torque on the rotor. Modern users, gyroscope tops are sold as a common toy. In addition to being used in compasses, aircraft, computer pointing devices, etc., gyroscopes have been introduced into consumer electronics. Since the gyroscope allows the calculation of orientation and rotation, designers have incorporated them into modern technology. The integration of the gyroscope has allowed for more accurate recognition of movement within a 3D space than the previous lone accelerometer within a number of smartphones. Gyroscopes in consumer electronics are frequently combined with accelerometers for more robust direction and motion sensing. Examples of such applications include smartphones such as the HTC Titan, Nexus 5, iPhone 5s, Nokia 808 PureView and Sony Xperia, and game console peripherals such as the PlayStation 3 controller and the Wii Remote. Nintendo has integrated a gyroscope into the Wii console's Wii Remote controller by an additional piece of hardware called Wii Motion Plus. It is also included in the 3DS, which detects movement when turning. Cruise ships use gyroscopes to level motion-sensitive devices such as self-leveling pool tables. Described as a motorbike car hybrid, the Lit Motors C1 two-wheeler uses a set of futuristic electronic gyroscopes, or control momentum gyroscopes, to ensure it remains upright and balanced, similar to the positioning technology used in the International Space Station and the Hubble Space Telescope. The only similarities the Lit C1 shares with the Segway is an IMU. A similar device has been used in the OYNO and Honda UX3 motorcycles. An electric-powered flywheel gyroscope inserted in a bicycle wheel is being sold as a training wheel replacement. See also, aerodrome, anti-rolling gyro or Euroship gyroscopic roll stabilizers. attitude indicator, balancing machine, bicycle and motorcycle dynamics, countersteering, Euler angles, Eric Laithwaite, gyro monorail, gyrocar, gyrotheodolite, gyroscopic exercise tool, heading indicator, hemispherical resonator gyroscope, reaction wheel, rifling, rigid body dynamics, top, turn and bank indicator, turn coordinator, LN3 inertial navigation system, stabilizer, vibrating structure gyroscope, references. Further reading, Felix Klein and Arnold Sommerfeld, Alberdei Theorie des Kreisels. Leipzig, Berlin, B. G. Tubner, 1898 to Euro 1914. 4v. Illas. 25 cm. Audin, M. Spinning Tops, A Course on Integrable Systems. New York, Cambridge University Press, 1996. Proceedings of Anniversary Workshop on Solid-State Gyroscopy. Kyiv Kharkiv. ATS of Ukraine 2009. ISBN 978-976-0-25248-6. E. Liamanis. The General Problem of the Motion of Coupled Rigid Bodies About a Fixed Point, Walter Wrigley, Walter M. Hollister, and William G. Dienhard. Gyroscopic Theory, Design, and Instrumentation, Provotidis, C.G. Revisiting the Spinning Top, International Journal of Materials and Mechanical Engineering, Volume 1, No. 4, ppA 71 Euro 88, open access at http www.imorgpdf/1397pdf. External links: The Royal Institution's 1974 Euro 75 Christmas Lecture, Professor Eric Laithwaite, One-Wheeled Robot Gyrostat by Olga Kapustina and Yuri Martynenko, Wolfram Demonstrations Project, The Little Top That Aims a Gun by Gold Sanders, Popular Science, July 1945, 8 Postoliuk v. Theory and Design of Micromechanical Vibratory Gyroscopes,